Okay, today we are going to talk about impulse. As we are going through this video, please make sure you pause it to keep up. Also, make sure you're listening to this. I will be explaining some of the concepts and not writing them down to kind of save on time. So let's go ahead and get started. So to start off with, impulse is just a change in momentum. And so remember, we can represent change in momentum with a delta P or a triangle P. If we're looking to derive a change in momentum from Newton's second law, what we can do is Newton's second law is F net equals mass times acceleration. Acceleration can be rewritten as delta V, or a change in velocity over time. So it's just our net force equals our mass times by delta V over T. We can then take our time and actually move it over. So we end up with something like this. So we have time times by our net force equals mass times by a change in velocity. And if you remember, we've already seen this mass times change in velocity that's already equal to our delta P. So if we write over in our formula box, we know delta P equals mass times a change in velocity, or we can also say it's F net times by T. A lot of these problems are going to require you guys using this. Sorry, I drew my arrow or my box over too far. Using this equation right here. So more often than not, we're going to be using m times by delta V equals F net times by T. Okay, so if we look at our first example, Luigi is sick of taking orders. He swings a 9 kilogram hammer at 16 meters per second when Mario's mustache brings it to a stop in 0.25 seconds. What is the net force exerted on Mario's mustache? So to start off with, we're going to go through and identify all of our pieces in this. So first off, we have our mass is 9 kilograms, which again, we're just getting right from the problem. We know our initial velocity, so the speed at which Luigi is starting to throw his hammer is 16 meters per second. We know its final velocity is going to be 0 because it says it brings it to a stop. So brings it to a stop. And then lastly, we know the time is 0.25 seconds because that's what it tells us. So first thing we're going to do is we're going to set up our formula. So we have mass equals a change in velocity equals F net times by T. So then we go through and plug in all of our numbers. So our mass is 9, our change in velocity. And remember, when you're doing change in velocity, it is going to be Vf minus Vi. It's always final minus initial. So our final velocity was 0. Our initial velocity was 16. And that's going to equal the force that we're going to be looking for times by 0.25 seconds. So that's our time. So if you rearrange this, so we divide both sides by the 0.25 to get F by itself, because then these two cancel, you end up with your net force being negative 576 newtons. And the reason why it's negative is because it's going backwards. So this tells us that our force that's being applied is being applied backwards. Okay, for the next problem. So you have a soccer player kicks a 0.450 kilogram ball at 25 meters per second east. If the goalie stops the ball by exerting 215 newtons of force, how long does it take to stop the ball? So we're going to forego the picture and then just talk about the different variables. So we know our mass is a 0.45 kilograms. We know our initial velocity is 25. They stop the ball, so our final velocity is going to be 0. And then lastly, our net force is going to be negative because that's the force that the goalie is applying. So it's the opposite of what the ball is going to feel. So the ball is going to have a negative force acting onto it. My pen. So first thing, we're going to start off with our formula. So we have mass times by our change in velocity equals F net times by time. Again, like I said before, most of the time we're using this equation right here. So we know our mass is 0.45. We're going to multiply that by 0 minus 25 because, again, it's final minus initial. And that's going to equal our force, which is negative 115, and divided by or multiplied by our time. So what we're going to do here is we're going to divide both sides by negative 215 to move that over to the other side to leave t by itself. When we do that, I already have that put in there. Then we end up with our time being 0.05 seconds. So for the next part, if the goalie stops a bowling ball, which is 6.5 kilograms, traveling at the same velocity in the same amount of time, how much force is required? So we're going to start by just coming up with our formula first. We won't identify all the parts. So our formula, again, is going to be mass times by a change in velocity equals the net force times by time. And since everything is being held the same except for our mass should change to be 6.5. Our change in velocity should still be the negative 25 or 0 minus 25. Our net force is what we are going to be looking for. And then our time is going to be the 0.05 seconds. So if we plug in our numbers, this is what our equation now looks like. We're going to solve for F. So we should divide both sides by the 0.05. So if I write this in, it should be a 0. I don't know if it's going to let me write this in here. Sorry about that. Head. Nope, it's not going to let me write it in. Anyways, so if we divide both sides by the 0.05, we end up getting negative 3,250 newtons. Again, the negative just tells us that it's going the opposite direction, which it should be negative because that's what our force was up above. Okay, for the next one. So coaches for many sports such as baseball, tennis, and golf can often be heard telling their athletes to follow through with their swing. How does this help a weaker player hit the ball farther than a stronger player? So first thing we are going to look at is we are going to look at our formula. So mass equals a change in velocity equals a net force times by time. So there's going to be a couple of things, if you're looking at the players, there's going to be a couple of things that are going to be held constant regardless of the player. So what we're going to consider constant for this one is we're going to consider the mass and the force. So we're going to assume, even though this talks about weaker players here, we're not comparing a strong player with a weak player. We're going to see how following through helps our weak player. So it's going to be the same force with the same mass because the ball shouldn't change its mass as you're playing. So what this is going to do is if you're following through, you're going to have more time with the ball. So your time is going to increase, thus causing our change in velocity to increase. So the more time in contact with the ball means or any object means a greater change in velocity.